All right, time to go on to part two of three. So we're going to define the center of mass this time, and talk about some of the interesting properties that arise out of defining the center of mass. So first thing that we do is note that instead of being a single particle, most objects are made up of multiple particles, millions and billions of particles that can uh that sorry that uh all can move with respect to each other, change with respect to each other, have internal forces. So when we're talking about this, we talk about Fj, which is the fraction of the force that the jth particle experiences, so that a single particle in the material experiences. So this is equal to Fj interior plus Fj exterior, which is equal to dpj dt. The force net is equal to the sum of all of these changes of momentum, which is equal to the sum of all the changes, the internal forces and the external forces. But if you look at the sum of all of the internal forces, then something that you should notice, or that should appear to you, is that all of the internal forces have to equal zero when you sum them up, because every internal force that you're going to see, that's force acting inside of the object instead of being acted upon by an external force, is going to be canceled out by another internal force per Newton's third law. So when you add them all out, there's going to be a negative internal force for every positive internal force that you experience, which means that you're going to end up only caring about the external forces, so sigma Fj. So F net is only going to be external forces, which is equal to the change in momentum over the change in time. So F net that's acting on the particle is only internal forces. So even if the it's not a particle, it's an object, first of all, but even if the object is moving, if it's spinning around, or it's a cat and it's moving its body so that it uh doesn't get hurt, or does that it's spinning or like moving its body in the air, then the only forces that are going to affect the momentum of the object are going to be the external forces. So that's getting a little bit ahead of myself, but uh, dp, we find p center of mass dt as the sum of all of the internal forces of all of the internal uh, momentums, and set that equal to ma, where m is the total mass of the object. So ddt sigma pj equals ddt sigma mj vj, which is ddt mj dr dt drj dt, which is d squared dt squared mj rj. So this tells us that the acceleration is equal to 1 over the mass times d squared dt squared mi r sigma mi rj, or not mirj, mjrj, which is equal to d squared d squared, which sets acceleration equal to d squared t squared of the average value of the center of mass, the average value of each mass uh, added together, times their uh, times their uh, position variable. So that's d squared dt squared r of center of mass. So this is the average value of the mass over r, in the same way that we were talking about um, f average being the average value of f over t. This is the average value of mass over r, or of r over mass rather. So this is an interesting this is an interesting property, and what it tells us is that r of the center of mass is never going to move or cause any acceleration except in when acted upon by an outside force. So if the cat's moving around, it's wiggling around, then the center of mass is still going to be accelerated according to say gravity or the outside force. But overall, the internal forces, the internal wigglings, are only going to aren't going to change the position of the center of mass. So only external forces are going to change the position of the center mass. So this is interesting, I think. This is why we can exclude internal forces when we're talking about Newton's second law, and why we can uh, just worry about external forces, and why we only care about external forces when we're solving these problems. So another thing to note is that the center of mass doesn't necessarily have to be uh, it doesn't necessarily have to be in the uh, it doesn't have to be a particle. It can just be the center of wherever the masses are held. So this is a thin ring. It's a little hard to tell it's a ring because it's uh, written out and it's kind of messy. But it's a thin ring, radius r, where the mass distribution uh, the center of mass is going to be equal to 1 over m times 0 to, or a to b, r dm, where dm uh d theta is equal or dm d some ds, which is the length along some unit quantity of the ring, the circumference of the ring, is equal to lambda, which is equal to m divided by 2 pi times r. So hopefully that makes sense. dmds is going to be the mass per unit length, which is m divided by 2 pi r. And then ds is going to be equal to r uh, d theta, where theta is the angle subtended, the angle that the mass is uh or yeah, the angle that the mass is integrated over. So dm, what happened to my screen? is going to be equal to lambda r d theta is equal to m divided by 2 pi d theta. So our center of mass is equal to 1 over m from 0 to 2 pi r cosine theta I plus r sine theta j. And then this is by m over 2 pi d theta, which is equal to 1 over 0, 1 over 2 pi from 0 to 2 pi r cosine theta I plus r sine theta j d theta. So Rx, our center of mass x, is equal to 1 over 2 pi, 0 to 2 pi, uh, r over 2 pi would be easier, cosine theta d theta is equal to r over 2 pi times sine of theta from 0 to 2 pi, which is equal to 0. And then our center mass y is equal to r over 2 pi 0 to 2 pi sine theta d theta equals r over 2 pi negative cosine theta from 0 to 2 pi, which is again equal to 0. So our center of mass is equal to 0 I plus 0 j, which makes sense even though there is no mass in the middle of the ring. It does the symmetry of the problem, the fact that there's mass always 1 r away, and that for every mass 1 radius away on the opposite end of the circle there's a mass that's going to cancel that mass out when you're adding the center of mass r dm. That's going to give you zero position for the center of mass, even though there is no center of mass at that point, or there is no mass at that point. And then for the final thing that I'm going to talk about for center of mass, we just have the Earth at the center of our coordinate system, so at the origin. And then the moon some distance away, distance rm away. And that is going to, and we're going to try to find the center of the mass between the moon and the Earth, even though the Earth, we're always told that the moon revolves around the center of the Earth. It's actually revolving around the center of mass of the Earth, and the center of mass of the Earth and the moon is where both of these bodies revolve around. So r, the center of mass, is equal to m Earth, r Earth, plus m moon R moon over M Earth plus R Earth, or M Earth plus M moon. Which is equal to M Earth times 0 plus MM, mass of the moon, times RM over ME plus MM is equal to 7.36 E 22 kilograms times 3.82 E 8 meters divided by 7.36 E 22 kilograms plus 5.97 E 24 kilograms for the mass of the Earth, which is going to be equal to 4.634 times 10 to the 6, or yeah. Okay, don't stop freaking out on me. Yeah, 10 to the 6 meters. So 4.64 times 10 to the 6 meters. Which is going to be around here. So instead of actually orbiting the center of the Earth, both the Earth and the Moon are orbiting their center of mass, which is going to be somewhere under the surface of the Earth. So the main thing that you want to learn from this is that even if you have a mass at r equals 0, you have to include it in the total mass. It just isn't going to be included. It just isn't going to factor into the numerator of the or numerator of the calculation, but will factor into the denominator. Okay, that's going to be all I have to say for center of mass. I'll have one more recording after this, so stay tuned.